Underneath an old farmhouse, there's a small dirt-walled room that kept an entire family fed through the coldest months of the year, with no electricity, no motor, and no moving parts at all. It wasn't a lucky accident. It was a genuine piece of engineering, worked out through trial and error long before refrigeration existed. And unlike most old technologies we now consider obsolete, this one is still genuinely useful today, not just historically interesting. This is documented agricultural history, USDA Cooperative Extension design guides, and the actual thermal physics behind one of the oldest food storage technologies still in use today. Sit with that for a second. A system with zero moving parts, doing a job we now dedicate an entire, always-running appliance to. In the next few minutes, you'll see exactly how a hole in the ground could hold a steady, safe temperature all winter, why some vegetables needed a completely different environment than others just a few feet away, and why this same basic principle is still being used today. It starts with a fact most people never think about. The ground beneath your feet has its own, mostly hidden climate. Before refrigeration, keeping food edible through winter wasn't a convenience question. It was survival math. A family needed enough stored food to last from the last harvest to the first spring crop, sometimes 5 or 6 months with nothing new coming in. Think about planning an entire winter's worth of meals in advance, with no way to simply restock if you got the estimate wrong. Here's the strange part almost nobody expects. The solution wasn't really about keeping food cold in the way we think of a refrigerator today. It was about finding somewhere the temperature simply couldn't swing very far in either direction, no matter what the weather above ground was doing. Air temperature outside could swing from well below freezing to unseasonably warm within the same week. That kind of swing ruins stored food fast. What farmers needed was stability, not just cold. Here's a detail worth pausing on. A root cellar that got too warm for even a few days could undo months of careful storage. Here's the part most people never hear about, where that stability actually comes from. A few feet below the surface, soil temperature stops tracking the air above it closely at all. Below the frost line, the depth winter cold actually reaches. The ground settles into a temperature that stays remarkably constant year-round, regardless of a heat wave or a cold snap overhead. This happens because soil has enormous thermal mass. It takes a huge amount of energy to change its temperature, so it simply doesn't change quickly. Compare that to air, which heats and cools almost instantly by comparison. That difference alone explains most of why a cellar works at all. The detail almost no one mentions is how deep that stability actually requires digging. In most temperate parts of the country, that frost line sits somewhere around 4 to 6 feet down, deep enough that a simple hole wouldn't do the job. A properly built root cellar is dug specifically to sit below that line, using the surrounding earth itself as natural insulation on every side. Many were built into a hillside rather than straight down, which made both digging and daily access dramatically easier for a family using it constantly. Here's where the design gets more clever than most people expect from a hole in the ground. Earth alone wasn't enough. A sealed underground room with no airflow would trap moisture and stale air, ruining food just as fast as temperature swings would. Well-designed root cellars included a simple ventilation system. One vent positioned low, near the floor, and another positioned high, near the ceiling. What no one expected was how much work that simple height difference actually did. Cold air is denser than warm air, so it naturally sinks. Warm, stale air naturally rises. With vents placed at both the top and bottom, the cellar could passively circulate air on its own, with zero mechanical parts and zero power, just by taking advantage of how air already behaves. The whole system runs on the same basic physics that makes a chimney draw smoke upward, nothing exotic, just consistently applied. USDA Cooperative Extension guides from across the 20th century described this exact two-vent principle as the backbone of a functional root cellar design. Here's a detail worth pausing on. Getting that vent placement even slightly wrong could undermine the entire system. Too little airflow, and moisture built up into mold. Too much, and the cellar lost the very temperature stability the whole design depended on. Here's the detail that surprised a lot of first-time cellar builders. Not every stored food wanted the same environment, even inside the exact same cellar. Root vegetables like carrots, beets, and potatoes needed high humidity, close to the point of dampness, or they'd shrivel and go soft within weeks. Farmers often packed these in slightly damp sand or straw specifically to hold that moisture level steady around the vegetables themselves. But onions, garlic, and squash needed the opposite: drier air and better ventilation, or they'd rot from excess moisture almost immediately. Notice what that actually required. Farmers weren't managing one storage environment. They were managing at least two, often in the same small space. Some cellars solved this with separate bins and shelving positioned by airflow and moisture level. Others built entirely separate rooms or structures for exactly this reason. Getting this wrong wasn't a minor inconvenience. It was the difference between food that lasted the winter and food that didn't. Apples added another wrinkle entirely. They release a gas as they ripen that can speed up spoilage in nearby potatoes, so experienced cellar keepers often stored them separately on purpose. Here's the part worth knowing. If you've ever compared this to a modern refrigerator has a target range that isn't far off from what a typical root cellar, built correctly, actually achieved, somewhere around 32 to 40 degrees Fahrenheit, held steady. The difference is that a refrigerator gets there with a compressor, a motor, refrigerant, and a steady supply of electricity running constantly. A root cellar got there with nothing but geometry, depth, and two well-placed holes for air to move through. Here's the last piece of this most retellings skip entirely. A refrigerator's temperature control is active, constantly working, constantly using energy to fight against the room around it. A root cellar's control is passive, built into the structure itself. Think about how different those two solutions actually are, even though the end result is nearly identical. One steady, safe temperature. No moving parts also meant almost nothing to break. A well-built root cellar could function for generations with essentially zero maintenance beyond basic upkeep. Some cellars still in use today are well over a century old, built by hands that never once considered electricity part of the plan. Here's what's worth knowing. If you've ever seen an old cellar door built into a hillside and wondered what it actually was, that structure represents a genuine engineering solution, refined over generations, to a problem modern households mostly never have to think about anymore. Here's the part worth sitting with one more time. Every piece of it, the depth, the earth walls, the two vents, was solving one specific documented physics problem, not just tradition for its own sake. Notice what actually made this work: not a clever gadget, but a careful, patient use of physics that was already sitting right there in the ground. The soil never needed power. It just needed someone to dig deep enough and smart enough to use what was already there. That's a genuinely different kind of engineering than most of what we build today, solving a problem by understanding it, rather than by adding a machine on top of it. That's the real story, documented in USDA design guides, and still used today by anyone who wants food storage that never needs a power bill. If you want more of these, the real documented engineering behind the things we take for granted on old farms, subscribe to The Quiet Farmer. Waiting. That's probably all an old, unused root cellar on your own property is doing right now, still perfectly capable of the exact job it was built for. And tell us in the comments, does anyone in your family still use a root cellar?